Welcome to IT Alchemy, where we decode complex tech into simple steps. In today's video, we are going to deep dive into one of the most fundamental infrastructure decisions in the modern IT world, which is bare metal, virtual machine, and containers. If you have ever wondered when to use what and why companies are shifting between these models, stay tuned. We'll break it all down. Every software application runs on some form of infrastructure, but not all infrastructures are created equal. Understanding how the infrastructures are set up, bare metal, virtualized, or containers, has a direct impact on performance, cost, scalability, and security. The three questions we will answer: what are the three models? What are the pros and cons of each of them? And when should you use each? Let's start off with the oldest and the most fundamental concept: bare metal. In simple terms, bare metal refers to a physical server or real tangible machine sitting on a data center or under your desk. There is no abstraction. You just run your operating system directly on the hardware. Think of it like a standalone house. It's like building directly on the ground. No pre-built foundations, no utility setup, just raw earth. You bring your own material, blueprints and technologies and tools. You are in full control, but it requires a lot of work and effort. So, in simple terms, bare metal refers to a physical server. Imagine a traditional data center. Each physical server runs one operating system and one application stack. So, the bare metal access to the entire resources of your server without requiring to share it with any other. When you power on the server, it will claim all the hardware resources like CPU, memory, and storage. Post that, you will install your operating system, which can be Windows or Linux. After that, you would be installing and deploying your libraries and dependencies. Post that, you install and deploy your application. The entire application, libraries, and operating system are installed on a single physical hardware. So you have got one operating system, one application, which is installed on your raw physical server. So this is basically what a bare metal is. Let's talk about the advantages of a bare metal server. The first one is dedicated resources. There is no sharing of CPU, RAM, or storage. Your full performance is of your workload on your hardware. You get the high performance. Ideally, for demanding applications like database, gaming, and video processing, full customization. You can install any operating system, hypervisor, or an application stack as per your needs. Enhanced security. The physical isolation, because one operating system is installed on one hardware, provides stronger protection for sensitive data and applications. Bare metals are cost effective for long term usage. It's more economical for sustained workloads when you compare that with the cloud VMs. So now let's see what are the disadvantages of bare metal servers. First one is complex to manage. It requires extensive configuration expertise, planning, and takes more time to set it up compared to virtual machines. The engineers needs to have a very good understanding of the underlying hardware, its dependencies, the prerequisites. That's an overhead for the engineers. It has a higher upfront cost and operational cost, and these costs are generally bared by a single user, especially if it's a high performance hardware. It has a limited scalability. You cannot dynamically scale up your resources, and upgrading requires manual intervention. So, for example, if you need to create a cluster with a similar hardware, it's going to take time and extensive planning. It's not easily self upgradable. It lacks the flexibility of a virtual machine that can quickly adapt to any changing capacity needs. like CPU, memory, or hard disk. Bare metals are powerful, but they are very demanding. Though they provide the high performance, but it's very complex to set it up and maintain them. What are some of the use cases of a bare metal server? First, it's the enterprise workload. For e-commerce, ERP, CRMs, it's extensively used, where you have bandwidth heavy workloads like gaming. Financial workloads, fraud detection, real-time risk analysis, and trading systems extensively use bare metal servers. AI workload, which requires GPU acceleration, high memory bandwidth, and parallel computing. Bare metal servers are extensively used in big data, business intelligence, and analytics databases. Business critical databases. Another use case is scientific simulations or resource hungry applications. Now that we have understood what are the use cases, let's proceed to understand what are the virtual machines. A virtual machine is a software emulation of a physical computer. It runs on a hypervisor like VMware, Hyper-V, or KVM, which lets you run multiple operating systems on a single physical hardware. Think of it like an apartment. Some resources or amenities are shared, for example, the hypervisor host operating system, by the application. Some amenities are still app specific, that is, the things within the guest operating system. It requires moderate maintenance. So let's deep dive into what virtual machines are. As you can see, the hardware. On top of that, you have the hypervisor, which in turn creates multiple virtual machines like VM1, VM2, VM3. The hypervisor boots and it claims all the hardware resources, that is the CPU, RAM, and your hard disk. The hypervisor then uses the hardware resources and carves them into a virtual versions of itself, that is a virtual CPU and virtual RAM. Then the hypervisor creates virtual machines and packs them into virtual machines just look exactly like the physical server. Once the VM is created, we need to install the operating systems, then followed by the applications and its dependencies. As you can see, each of the virtual machines have their own virtual resources, like your virtual RAM, CPU. Within each of the virtual machines, VM1, VM2, and VM3, each of the virtual machines have their individual operating system. Some of them have Linux, while some has Windows. Then on top of that, you install your specific applications. So what are the advantages of the virtual machine? Effective resource utilization. You can run multiple VMs on a single physical machine, therefore maximizing the hardware. As you can see, VM1, VM2, VM3 are run on a single physical server. Easy backup and recovery. The virtual machines provide various capabilities like snapshot, clone, or backup. You can easily take each of the virtual machines and then clone it up, or you can also take a snapshot of each of them at runtime. Isolation. Each VM is isolated from each other, enhancing the security and fault tolerance because they have their own operating system, so they don't share the kernel with any other servers. Flexibility. It supports different operating system. You can install Linux, Windows, or any other operating system based on your application needs on the same hardware. So multiple operating systems can run on a single machine. Portability. VMs can be moved between physical hosts or data centers with minimal downtime using capabilities like vMotion. Now let's see what are the disadvantages of a virtual machine. One is performance overhead. Hypervisor layer adds latency when you compare that with a bare metal server. Licensing and cost. The licensing fees for the commercial hypervisors are an overhead. Also, when you have multiple operating systems like Linux or Windows, you also incur the licensing cost of those operating systems. Slower boot time. Each VM has a full operating system And because it's booting from the operating system, it's going to take a longer time comparing that with alternatives like containers. High resource consumption. As we mentioned before, each VM creates its own virtual resources like virtual CPU, virtual RAM. Each VM runs on a full operating system, plus it has its own memory and CPU. Storage overhead. Snapshots backup take a lot of space. Also, the large disk based on the operating system. So, what are the use cases of a virtual machine? It's extensively used in training and education, wherein you can build up systems, do some POCs. It's used in server consolidation when you want to bring a lot of servers into a single data center or a single rack. When you need to run multiple operating system environments, you can run containers on a virtual machine. Virtual desktop environments are extensively using VMs. It's used in disaster recovery and business continuity, using snapshots, backups. Finally, we have the containers, the rising star in modern infrastructure. Containers are lightweight, portable environments that share the host operating system's kernel. If virtual machines are like rooms in an apartment, think of containers like rooms in a hotel. A hotel has a better control over managing resources. The guests only have a subset of amenities which they can use, and most of the amenities are shared. Similarly, containers are lightweight, portable environments that share the host operating system kernel. Tools like Docker, Podman, and orchestration platforms like Kubernetes have made containers really popular. A container is a self sufficient package which has your application code, your application configs, your libraries, the necessary tools, and application dependencies, and finally the runtime. And they bundle that into a software package. Because the container has the code, its dependencies, and its configurations, the application behaves the same no matter where it runs. If you run the container in dev, production, your laptop, or your cloud, it will run the same no matter where. Because the container shares an operating system kernel, it's lightweight, fast, and efficient. Let's deep dive into what the container model is all about. As you can see, power on the hardware, you have an operating system which is running on it. The operating system boots up and claims all the hardware resources like CPU, RAM, and the hard disk. Then you install a container runtime like Docker, Podman. To deploy an app, you ask Docker to create a container. The container uses the operating system resources and carves up the process tree file system into virtual machines and then packages them as a container which looks exactly like a regular operating system. And then your application runs in that container. You can install multiple containers on a single machine and they all will share the operating system kernel. What are the advantages of a container? They are lightweight and fast. Containers share the host operating system kernel, thereby minimizing the overhead. That's why they are very fast and efficient. Portability and consistency across environment. The philosophy of a container is build once, run anywhere. Because the container has the code, the dependencies, you can run it in any of the environment and it will behave the same. You can run it in dev, test, production without any changes. Scalability. You can easily spin up or tear down a container for microservices or auto scaling. You can stop container 3, you can spin up a container 7 with a different application or the same application. Isolation. Each container runs on its own isolated environment and limits the impact of a crash or a breach on one of the container. It is still a limited isolation when you compare that with VM or a bare metal. It has a smaller attack surface area compared to a full blown operating system. Cost effective. It reduces infrastructure and licensing cost because each container is sharing the operating system kernel. They don't incur the cost as compared to a virtual machine. Now let's see the disadvantages of a container. The security isolation, not strong as VM. Because the containers share the operating system kernel, if the operating system kernel is compromised, it will impact all the containers which are running on that host, and all the containers will be at risk. Complex networking. Advanced container networking like overlay, service discovery, ingress can be complex to set up. Containers has to connect with other containers within the server and beyond the servers, and that can be a bit complex to set it up. Performance overhead. While containers are very lightweight, but when we use orchestration platforms like Kubernetes, they can still introduce overheads. Steep learning curve. This requires learning Docker, the orchestration platforms like Kubernetes. Container securities take time. Also, troubleshooting is very different than the traditional systems. Containers are not idle for all workloads, like the monolithic legacy applications or apps that require a full blown operating system. Now that we have seen the disadvantages, let's see some of the use cases of a container model. Containers are extensively used in the microservice architecture. They are isolated, lightweight, and easily scalable. They are used in edge computing to deploy lightweight containers for real time, low latency processing. They are the de facto for CI/CD pipeline. They provide seamless integration to build, test, deploy workflows to speed up the release cycle. They are extensively used in development and testing environment. You can quickly spin up a clean, repeatable dev and test environment without affecting the production. Now that we have understood what bare metal, virtual machines, and containers are, now let's see a quick comparison between them. So, in terms of performance, the bare metal provides the highest performance, followed by virtual machine and the containers. Isolation is the strongest in the bare metal, followed by virtual machines and in containers. Bare metals have a slower boot time compared to virtual machine, whereas container it boots up very quickly. Resource utilization is excellent in containers, whereas good in virtual machine and poor in bare metals. Bare metal has a low portability comparing that with virtual machines, whereas in containers the portability is pretty high. The management of a bare metal servers are pretty manual. In virtual machine there are various tools which you can manage the VMs. Containers can be highly automated to manage them. Let's do a side-by-side comparison of a bare metal versus VM versus containers. In bare metal, one operating system is installed on the hardware. In virtual machines, the hypervisor is installed on the hardware. The hypervisor installs multiple VMs with different operating systems, and each VMs have their own applications running on it. In container, a Docker engine or a container runtime is installed on the operating system, and the container runtime will spin off many containers which share the operating system kernel. You can run a lot of containers on a single physical machine with different applications. As you can see, the containers provide an effective utilization of the underlying physical hardware. Let's summarize the real world use cases. Bare metal servers are extensively used in gaming engines, large databases, and big data. Virtual machines are used in enterprise applications, compliance heavy systems, and especially multi tenant hosting. Containers are the de facto for microservices, for SaaS platform, CI/CD pipelines, and fast prototyping. Now that we have understood what are bare metal servers, virtual machines, and containers, so what is the verdict? If you need raw performance, bare metal is the way to go. If you need multiple operating systems with different applications, you need to go with the virtual machine. If you need fast, scalable deployments, then container is your pick. Final thoughts. In 2025, most of the infrastructure are hybrid. Containers run on a VMware which is running on a bare metal servers. You can see hypervisor installed on a hardware which then spins off multiple virtual machines VM1, VM2, VM3. Each VM has their own virtual resources like CPU, RAM, and hard disk. We can install different operating systems on them. on which Docker engine is installed. Containers are then run on each of these platforms. Tools like Proxmox, Kubernetes, and OpenShift are extensively used to manage complex environments efficiently. In today's cloud native world, it's not about choosing one technology over the other. It's about choosing the right tool for your job. Many organizations use a mix of all the three. The future is composability, and these decisions are made based on the performance, security, and the agility of the platforms. So, whether you are a DevOps engineer, a system architect, or just curious about how modern infrastructure works, understanding the difference between bare metal, VM, and container is the key. If you have found this breakdown helpful, give us your like, drop your questions or thoughts in the comments, and don't forget to subscribe for more deep dives like this.